First of all, welcome to today's episode of tinyML Talks. My name is Danilo Pau, and I'm very pleased to introduce you Varun Chari, staff software engineer in Arm. And before to leave the floor to his presentation and to his speech titled Streamlining tinyML Application Development Using open-CMSIS and Visual Studio Code, let me remind a few things which are important. First of all, tinyML Talks, such as other initiatives organized by the tinyML Foundation, are possible thanks to the great support of the strategic partners and their commitment to support such an event, as well as many other initiatives. Let me remind them one by one. AI-Zip, Arduino, Arm, BrainChip, Edge Impulse, Embed UR, Efficient, Greenwave Technologies, Gravity, IMAX, ImageBob, Infineon, Innatera, Nota AI, NXP, PNG, PIMIC, Polin Technology, Corvo, Qualcomm, Renesas, Schneider Electric, Sensimil, Sony, Silicon Labs, ST Microelectronics, Synaptics, Syntiant, TDK. It's very important also to keep in mind and to remember the initiatives such as the Meetup and the LinkedIn community, which are very important for the tinyML community we all serve. The Meetup essentially are a great asset in order to let groups at national level, at local level, located in different countries, to meet in a very simple and productive way to implement networking and to exchange development ideas and exchange also latest advancements and essentially have the possibility to talk each other and to interconnect each other. It's a very well-populated community, more than 20,000 members. And the other community is the LinkedIn community, you know, one of the preferred networks from a professional point of view. So many of the news and initiative of tinyML Foundation are communicated also through LinkedIn. So consider to join the community if you are not already in. In terms of content produced since the establishment of tinyML Foundation, YouTube channel of tinyML has been a great repository of know-how. So let me make an example just to underline the importance of this channel, especially in the last few weeks. If you are seeking to knowledge on generative AI, tinyML Foundation and the community behind the tinyML Foundation organized a very important knowledge sharing at the end of March and during the summit. So you may find many of the speech of the forum of the generative AI forum on the YouTube channel. And this is an important example, complemented by many other examples on how the community exchange the knowledge, the experiences also through YouTube. So if you are looking to stay to knowledge and to stay up to date on the latest development, such as generative AI, definitely pick up the content from the YouTube channel if you are not already in. tinyML EMEA is approaching very fast. We will be in Milan, Italy, end of June, 24th to 26th. So please register. There will be a very exciting agenda which has been published with the keynote speeches of very important people, as well as many experts in tinyML community that will exchange and will share their vision, knowledge. So it's important that you consider attending, and I'm strongly encouraging you to travel in Milan and to really attend to this European event. So without further delay, let me introduce Varun Chari. Varun is a software engineer in Strategic Alliances Technical Marketing team at Arm. He focuses on enabling and leading software strategies on emerging technologies relevant to Arm across the strategic partners, such as Google, Meta, Amazon, Microsoft, in machine learning and IoT space. So thanks again, Varun, to be with us today, and I look forward to your exciting speech. To you, the floor.
Yeah, thanks, Danilo. I'll be presenting about how we can streamline tinyML application development using open-CMSIS packs and Visual Studio Code. So before beginning, what are the current challenges that we face while developing a tinyML application? So as you guys might be aware, these are some of the top challenges that we face that embedded software developer usually faces while developing a embedded machine learning application. So there is a lot of fragmentation currently in the industry. There are a variety of tool chains or IDEs from different silicon providers. For example, if you are using products from one silicon provider and then decide to change to a different silicon provider, you would have to go through their tool chain and their IDE to port your entire application and production chain to that silicon providers. And another challenge is there is a lot of duplication in the market right now. So for example, you have to get a copy of the code base for different projects into the single project and then build your project on top of that. Then there is a lot of vulnerability. You don't know where the open source or the unmaintained software is coming from. It might be a security risk to your tool chain and your production flow. And another thing is there is no modularity right now. All the embedded applications are, most of the embedded applications are monolithic. You have an entire project and everything builds on top of another. There is no agile way of developing these projects right now. And as the industry is moving more towards ML ops and CI/CD integrations, deploying these applications or these products at scale can also be challenging sometimes. Another reason these days everything is moving towards a cloud connectivity. So integrating cloud connectivity into your project also becomes a tough challenge. And there are a lot of solutions around it, but it can be challenging. Another thing, it's security. As I mentioned earlier, vulnerability and security, those are most of the concerning factors here. So what we can do in this case? So Arm has come up with this thing called CMSIS, which basically means Common Microcontroller Software Interface Standard. So a brief history about CMSIS. Arm started this with few silicon providers like NXP, ST in the beginning, Atmel, Luminary, Micro, NXP, and ST back in 2008 to have a common interface, software interface standard across ARM Cortexes. So we started in 2008 with an access to processor core, interrupts, and peripherals. Then as and when the industry demanded changes to these standards, we kept on evolving. Then in 2010, we had CMSIS version 2, which provided some optimized DSP compute functions for all Cortex-M cores. Then we had some debugging functionality added to it using peripheral debug descriptors. Then in version 3, we added some RTOS support for various RTOSs relevant at that time. And then in 2014, with CMSIS version 4, we added support for different middlewares like various peripheral drivers, RTOS interfaces, and these can be delivered using CMSIS packs. I will describe more about what CMSIS pack is and other things during my talk. And then again in 2016, we released version 5, you could develop open source the CMSIS packs using GitHub. Then we added support using CMSIS NN for machine learning. Then with Arm V8, we added support for Helium and also optimized CMSIS packs, Arm provided CMSIS packs to enhance machine learning on Helium cores. And then recently in 2023, we released CMSIS V6, which built upon that. We added support for CI, CD, MLOps, and ID integration like VSCode, which I would be also talking about in this talk. So as of now, we have more than 10,000 supported devices using CMSIS packs from 900 plus packs with 60 plus vendors, 6 million GitHub projects which are using this CMSIS packs and support multiple tool chains like GCC, ARM, CLang, and IAR and LLVM. So a brief overview about CMSIS. So this is like a very high level view of CMSIS, how it really translates into layers of into the application or the firmware you're building. So you have an application code at the top, and then there are various CMSIS drivers or CMSIS components that we call it, which interfaces with the application code, which in turn talks to CMSIS core, which are processor cores and peripheral cores, and which in turn talks to a system on chip and gets you the results. So the main thing is these all CMSIS drivers, CMSIS RTOS, these are all standardized interfaces. So the silicon provider just need to provide their implementation, and these are standard interfaces. So the application code is agnostic to the way the silicon provider is implementing the peripherals. So they just have the visibility to the API that is being shown by the CMSIS components, and they can easily start developing that. They don't have to learn and they don't have to basically learn different APIs from different silicon providers. They can use the standardized APIs to interface with the peripherals and the code. And on top of that, we provide CMSIS provides various command line and project build tools. Then there is something called CMSIS Stream, which is used for data streaming for ML and signal processing, which I would also go in detail later during my talk. And there are CMSIS packs, which are basically, think of it like Python pip Python pip repository or artifact thing, which you can just get into your project and start building the project. So that's about it. And we can talk, as I was saying, about the components. So what are CMSIS middleware components? So think, for example, middleware like file system, USB network. These are the base standardized middlewares that are being used in the industry, right? When you develop a embedded application. So this middleware uses all the standard APIs like CMSIS drivers, CMSIS compilers, CMSIS views, CMSIS RTOS, which can be just standardized. So the silicon providers just need to implement this file system using the APIs exposed by the CMSIS driver, and which supports other basic connectors like synchronous data streaming and IoT connectors, which basically helps you develop your application in a faster way because APIs are standard. There is no fragmentation, there is no duplication. So it's there is not much of a big learning curve in this case, and you can start developing the application easily. So this is more detailed view about the CMSIS driver interface. So you have your user application at a high level, then there are generic middleware components like USB driver, USB host, networks, file systems, graphics, and other interfaces. And so as a part of CMSIS pack or CMSIS component, all these interfaces, the control structs, these are basically standard control structs. So for a GPIO interface, these structs are standardized. So you don't, the application just has a view of this GPIO or USB interface or control struct, and the silicon provider basically in their device support package as a CMSIS pack implements the control using these control structs. So the application developer is really doesn't have to worry about different control structs from different silicon providers. They have a standardized control struct. They just have to configure the device pins based upon the silicon providers, and then that is also provided as a pack or as a part of the CMSIS software component, and they can just bring up an interface very smoothly and easily. So yeah, there is a unified API flow, similar design across all peripherals. Driver templates provides code skeletons, so you can just put in your implementation inside those skeletons and expose that peripheral to the application developer. Yeah. So what is a software component? I was talking a lot about CMSIS software components. It's basically an XML framed information used by the project management utilities from various tools. So think of like this example. You have this software component. For example, think of it like a Ethernet driver or a device support package from a particular silicon provider. So it has various API headers that are basically required by the standardized CMSIS. For example, Ethernet driver, you have RX, TX, the control structures for RX pins, the RX buffers, TX buffers, and all those things. So those are standardized APIs that are exposed. And then you have to provide some version and licensing information. And the code and source libraries are basically the implementation part of it. And you can have multiple software components feeding into this code and support. So a high-level device support package can have high-level APIs, and then they have in turn it can use peripheral APIs and peripheral software components like Ethernet, CAN, GPIO, and other things, and they in turn can feed into this software component, and then you can have a very hierarchical and nested structure in this case. So these are some of the basic necessities of a software component. You should have a version and history, licensing, API definition, because documentation is really important because we are standardizing it. Documentation plays a very important role for an application developer to understand how it really does. Then source files and configuration files, they are optional, but we highly recommend you have that because it again gives flexibility and details. And then requirements to other components. If one particular component is dependent on other component, then you need to define the dependencies. There is a lot of information about this on the web. You can easily go on and search for open-CMSIS pack specifications, and you can really get into detail about what it really entails and how to design a pack. So as I was mentioning, a different kind of different way of implementing a CMSIS software component would be central API definition. So silicon provider can also have a common the most common problem is API headers evolve over time, so we can have a consistent APIs over different versions. So a central API definition shares the header file, documentation across multiple other software components to ensure consistency. The actual implementation can change, whereas the API can be standard. I mean, this is what we see at the higher level programming languages or higher level software development, wherein the API really remains the same across different versions, just the implementation changes. This was not the case earlier in the embedded system space, but now with CMSIS, you can really do that for us. Yeah. So the API interface is distributed separate or as a part of software component that defines this interface. Therefore, the API header is consistent. Whichever the version changes, then just have to check the version and get that particular version pack if you are using. So a good example would be a CMSIS driver pack that contains various Flash, Ethernet, and Wi-Fi drivers. All are compatible with the standard CMSIS driver APIs. So if a silicon provider implements that driver interface across different version of their platform, the CMSIS driver pack will remain consistent, and the application developer can easily access to this particular CMSIS driver pack and develop their application and choose the version he or she wants to use depending upon the documentation and start developing their application. So basic example you could see here is the MDK middleware that Arm has developed. So we have this CMSIS component called MDK middleware CMSIS pack, CMSIS driver pack, which has interfaces for all the standard interfaces like network, USB, file system, embed TLS. In this example, you can see here we have like for device storage, you have memory card, which is implement the tiles or ARM's implementation of the middleware pack. So you can choose this. You can look at the documentation using this link, which is part of the source, and you can look at various APIs that are exposed by it and start using it instantly. So as you can see, this is more interactive way of developing rather than looking at the PDF file and the technical reference manual of a silicon provider and using that. And you can also select various versions of this driver. So for example, if we want to choose instead of 6.15.3, we want to use 5.15.3, we can just click on it, modify the version and start using that. It's more interactive and more user friendly. So I think there is a question in here. So from Matthias is asking, how would you define the relationship between CMSIS and Zephyr? So Zephyr is another one of the open source RTOS. So we have, like I mentioned earlier, so we have this CMSIS pack called CMSIS RTOS, which is basically an abstraction layer over all the RTOSes. So right now, free RTOS and Zephyr is supported, so you can download this CMSIS RTOS. You can get the CMSIS RTOS pack, an abstraction over Zephyr, and you can really start developing using CMSIS RTOS 2 APIs, and in turn it will translate those things to a Zephyr OS backend, and you can start developing that. So yeah, there is another question from Christine about if you can just show a practice example, some on-device training on a Raspberry Pi. So yeah, I have a demo with explaining all these things with how the CMSIS pack is integrated into a VS Code. Coming up, I would be demoing on ARM fixed virtual platform and actual board. It's from ALF, which uses ARM Cortex M55 and Ethos U55 for and I would be demoing a simple object detection machine learning example on that. So yeah, stay tuned, Christian. So yeah, going forward, so this is the basic overview about the CMSIS packs, the middleware, how you can configure those middlewares and also use them in your application while developing an embedded application. So there are a lot of software packs provided for different use cases. Like for graphics, we have CMSIS packs from LVGL, Embedded Wizard, and Sager. There is a lot of middlewares from AWS, especially around FreeRTOS, TCP, FreeRTOS OTA, MQTT agent, and all those things to provide connectivity to cloud. Then there is also from Mongoose, which provides a very lightweight web dashboard running on an embedded system. Then there are middlewares from ARM, Oryx. Then there are SSL security CMSIS packs from Wolf SSL and Embed TLS. There are a lot of machine learning or DSP from Edge Impulse, TensorFlow, Light Micro. It's another CMSIS pack which can be used for machine learning, which would be very much interesting for this particular audience. There are a lot of RTOSs, like I mentioned. There is Zephyr, there is Kyle, Embed, FreeRTOS. There is also a lot of other really good CMSIS packs which can be used for debugging and an application. And a lot of silicon providers have their own device support pack as a CMSIS pack, like NXP, ST, ALIF, all have their own CMSIS packs, which basically defines the interface to peripherals using CMSIS drivers and other standardized CMSIS packs. And from ARM, we have a lot of other CMSIS packs like CMSIS DSP for accelerating some of the functions for signal processing, SIMSYS NN for using Helium technology on ARM V8 for machine learning, SIMSYS RTOS, SIMSYS View, Stream, and Compiler for debugging and meta visibility. So yeah, now let's talk about this overview about SIMSYS packs. So this is well and good. You can just do all these, get all these packs using SIMSYS packs, using the CLI tools that are offered, and start developing using whichever IDE you prefer, whether it is ARM DS, MDK, or simple Notepad or Vim, whatever, or even a CMake project if you want. But then later on, ARM did a market survey and figured out that this is all and fine. Now, the most widely used IDE in the industry from a developer perspective is VSCode. Whatever we start developing, we just open VSCode, even if it's like text editing a text file on a remote connection. I just basically, my personal opinion, I just open VSCode, create a remote connection, and then start editing the file. So VSCode has developed like a most widely used IDE in recent times. So ARM decided to create a extension pack in VS Code called ARM Tile Studio Pack, or ARM MDK, which was previously called, which comprises of various different packages that I mentioned, like for SIMSYS Solution, Embedded Debugger, Embedded Environment, and other ARM tools inside a single extension pack. So it's basically a comprehensive software development environment for embedded systems and IoT software development on ARM-based MCUs. It has various VS Code extensions, plug-and-play device support for debug probes and development boards, access to SIMSYS pack ecosystems, and integration with open-CMSIS packs. So you don't have to really go into terminal and type access the CLI tools. You can do everything interactively using VS Code, Tile Studio Pack, or various ARM extensions. So think of it like you're developing a ML application at a high level in VS Code, and then when you decide to deploy it on a target or develop on the edge, then you just change into a different IDE. Now you don't have to do that. You can still stay in VS Code, be in your friendly environment or a known environment or a known IDE, use all the IntelliSense and everything that VS Code offers, and start developing that. So if you have integration with GitHub Copilot or Amazon VSCode Whisperer, Amazon Q, or other AI assistant, you can also easily leverage those aspects of it and code increase your productivity. So these are the various things that Tile Studio Pack really offers. Some of the essential VS Code extensions that are thing. So like SIMSYS csolution, as I mentioned earlier, it is mainly used to create and manage SIMSYS-based projects, which offers SIMSYS Toolbox, compiler, various compilers, as I mentioned, ARM Compiler 6, TCCLLVM, license manager for activating the ARM compiler. Then the environment manager is basically to manage your environment. So it's basically agnostic to your host machine. So you just have this environment figured out as a JSON file VC package. It uses Microsoft VC package tool in the background to create a virtual environment or an environment, and then start developing it. So it's basically helps in portability. You don't have to be dependent on your single host development machine. In this case, you just configure your VS Code using VC package environment manager and install all the necessary tools. And even if you change the host machine and clone this particular project into a different host machine, it will automatically pick up this environment, and you can start developing from there. So it's basically helps speed up portability and productivity. There is support for CLangD, which basically helps in IntelliSense, like auto-completion, suggestions, and everything. And there is some YAML support because all the C solution and everything is YAML based, like XML configuration files. So it's YAML based, and it helps in configuring these projects. And there are other debugging extensions like Arm Debugger, which is basically used to debug Cortex-M and A processors. There is Device Manager for managing all these device connections to the Cortex-M through the Ulink Pro, SIMSYS Tab protocol, ST-Link, fixed virtual platforms, and other debuggers. So yeah, what is an, as I'm mentioning, there is environment manager. So it's a part of VS Code extension. All the development environments are managed through Microsoft VC package tool. So here we have created a registry. Arm has created a registry for all the Arm-based SIMSYS packs. So you can just get the SIMSYS packs from there. Just include this VC package configuration file in your project and specify these repositories, and you can pull in the SIMSYS packs from here. So this again provides you the portability and flexibility to work from any development environment if you wish. And the next is the SIMSYS toolbox. So again, this is part of Microsoft VS Code extension. It's based on SIMSYS standards. So it can be individually or as a, excuse me. It has support for multiple compilers like ARM, CLangD, GCC, IAR. It also has support for CLI tools. If you're comfortable using CLI, you can do it using CLI or even interactively using the csolution extension. And it supports almost all major host operating systems like Mac OS, Linux, and Windows. So one of the earlier challenges that was being faced by embedded developers was most of these IDEs and tool chains were only available for either Linux or Windows. So they hadn't had the flexibility to develop on Mac. So now you can even get this VS Code installed on a Mac, get this your environment set up using environment manager and SIMSYS packs, get the SIMSYS packs, create a virtual environment basically, and then start developing on any operating system you wish. So this is a high level overview about the SIMSYS solution. So this is how it basically, when you open a project, configure a project using SIMSYS pack, the VSCode VC package configuration, you have configured it, and you have some basic csolution files. So these are the standard things that you need to provide in this case. You have a solution, the build type, which compiler you are using, what are the components. These are standard things you provide as a part of your CMake file, right? You have set their environment variables and everything. Now this is more interactive and more indented. So you have what type of build you are using. You can select the context, which kind of project. You can have multiple projects inside a single solution. You can detect the hardware using Arm Device Manager. You can manage related projects. You can build, flash, and debug everything interactively from a single UI. You have different project actions, like I mentioned. Then you can manage all the SIMSYS packs using the software components thing. You have IntelliSense integrated using CLangD and YAML. So it shows you quick solutions about what type of error you are making and what are the quick fixes. That's a very easy, very productive tool from VS Code. Then you can also validate all the SIMSYS packs right from VS Code itself. And if you want, if you are more into using terminal, you also have a CLI tool wherein you can access all these things using CLI. So again, deep dive into the same things. You can validate all the SIMSYS packs that you are using, the dependencies, so you can really pick and choose from interactively and not go inside, configure multiple CMake files, and then provide a link to different CMake files if you are using a CMake based project. This is a plus point over using a SIMSYS based solution because it's more interactive and more user friendly. So high level software developers are not really well equipped or well knowledgeable about CMake and the intricacies of it. So this really helps them clear the barrier to entry and be more interactive while developing an edge or embedded ML application. Again, you can choose different versions of the CMSIS packs and then whichever your project demands and go through the configuration. Then you can really do rapid prototyping because it's easy. You can really drag and drop files and they will instantly become part of your solution. You don't have to modify anything per se. And then it's really easy to create a new CMSIS solution interactively. You just select which type of board you want, which device, and all other things are basically made more user-friendly than you being authoring all those things. So to accelerate ML application development, ARM has also provided a basic CMSIS pack in the form of ARM ML evaluation kit. It basically provides a low barrier to entry through ML application, standard ML applications or examples or demos. So it enables users to understand and experiment with software stack. It enables performance evaluation for model inferences, enables users to try custom workflows, networks for new use cases. So it's basically an easy entry for ML application development using the entire open-CMSIS and the VSCode ecosystem. And then it also provides you to bring in your own model and build your own application around the model using the underlying stack. So we have, it also provides a very easy interface to TF Lite, TensorFlow Lite runtime for microcontrollers. It is also available as a CMSIS pack. It offers basic use cases like anomaly, person or object detection, keyword spotting, speech detection, noise reduction, offer supports for logging and other math functions. And also we have also a pretty standard model zoo for all the above use cases. You can use those model zoos and start building your own application. These are all open source, by the way. So this is the basic high level view about how you would go about developing a ML application using your ML eval kit. So we have a user application here, which basically looks at the ARM ML eval kit APIs, which in the background looks at TensorFlow Lite Micro to run the ML inferences. So TensorFlow Lite Micro can use ARM CMSIS to accelerate the operators on an ARM-based platform, or they can also use something called Ethos U driver, which basically targets the NPU if you have an NPU in your system. You can use CMSIS DSP for some device signal processing, ARM2D to do some graphics, LVGL to do some graphics too, and then the device support package from your silicon provider can be used to interface with all these components using the user application. So basically this provides you a faster agile development, avoiding duplication, leveraging and integrating existing solutions. So you don't have to write your own source code for all these things. You can just get those CMSIS packs and start developing in VS Code. So yeah, let's look at a simple standard example. So in here, yes, you can see this is one of the same example projects that ARM provides. It's called CMSIS example. ARM CMSIS example. It's easily available on GitHub. ARM CMSIS pack example. So in here, this is the CMSIS extension I have installed, and you have the visibility of your entire project in here. What groups are there? What device files like the scatter files or the map files that you use? All the layers that are used, all the CMSIS packs. So if I go to this software components tab, yeah. So if I go to the software components pack, you can see all the CMSIS packs that are available for this particular target platform. Like what are CMSIS drivers, what are accelerators available, the DSPs, the everything. I have really, you can pick and choose whatever you want to install. Like for machine learning, in this case, I have enabled the NPU support for the Ethos driver and then the TensorFlow Lite support. Then I have included ML eval kit examples in here, for example, the common things and the object detection in this case, then all other BSPs that are available, external peripherals, that are standardized CMSIS drivers for different peripherals, so on and so forth. So you can easily pick and choose from here interactively, and the corresponding YAML file for the project configuration will be updated. You don't have to update it manually. If you wish, you can also update it manually using different things, but it's not really necessary. So this provides a very easy user interface and removes that barrier to entry. So yeah, Mitchell, Christine, you had a question about this thing. So does that she also asked about the CMSIS compatible with EdgeImpulse. So I'm not sure if EdgeImpulse offers a pack to this. Does the ML eval, there's one more question about from Matthias. Does the ML eval tool allow me to build and distribute ML applications? Is there license free? What is it eval? So yeah, I mean, ML eval kit, you can. It's an open source basically eval is evaluation. So it's a CMSIS pack. You can, either you can use it as a part of the csolution, or you can also do it using CMake. It's basically how you can leverage ARM accelerators like Helium in V8 or even Ethos U to build your ML evaluation ML application, and we provide basic models from Model Zoo like YOLO V3 for object detection and some other mobile net SSD, even for classification and all those things. So you can get those tools. It's license free. You can download it right now from GitHub and start developing your application on top of that. So yeah, I mean, if you have configured all those things, now you can go manage solution. You can select what type of hardware you want to deploy the application onto. In this case, I am using, for example, I had built this project initially on an fixed virtual platform. And then, for example, if you change the hardware now to a ALIF E7 board and you want to build object detection using in a debug configuration, you just have to modify all these things here very interactively, and you can just build the project, and it will start building the project. It will look at all the dependencies, and if there are something missing, it will throw an error, and you can easily fix it using the interactive tool here. And once it builds, you can easily see the progress here, and it would create an output file in the output directory. And since this is VSCode, you can easily configure your tasks. Like you don't have to go through another IDE to Flash. You can easily do it programmatically by configuring VSCode task.json to pick up the build binary from here and deploy it onto your hardware using the you can provide a Flash tool if that is different from what ARM has provided as part of this. So you can see here it's built from I had built it earlier, so it didn't go through the entire process for the sake of the presentation. It built without any error, and files are available in the out directory. So you can just go in here, and you can see all these files are available here. Bin and exec files. You can deploy this onto your application, onto your board, and test it out, either debug or deploy it automatically. So there is another follow-up question from Christine. Does it cover other frameworks aside from TensorFlow Lite? Also, can I do distributed training with it across machines? So right now, there is only support for TF Lite because that's the most widely used runtime on embedded systems or in a microcontroller space. Can I do distributed training with it across machines? So training as such, we don't really do training on an embedded systems, right? We just do inferencing. Across machines, of course, you can build a project using all this ecosystem across for different platforms and deploy it onto different platforms. As far as training is concerned, I'm not sure if you really do training on this embedded systems. You just do inferencing. So the power consumption, another question from Joseph. What is the power consumption for inferencing? So it also, you can have the CMSIS pack provides profiling tools. You can profile the power consumption using those CMSIS packs. And if you have the device implements those protocols, and the device support package, device firmware package implements those profiling factors, and you can really do inferencing on it, or else you would have to go to the silicon providers tool to do the power consumption and other profiling for the application. So yeah, what are the other ML tools that ARM really offers in this case? So we have, as I was mentioning before, we have something called fixed virtual platform. Those are basically a virtual platform about a reference implementation of our ARM-based microcontrollers and neural processing units. So you have fixed virtual platforms for bare metal or OS hosted environment for Cortex-M and Cortex-A. There are Cortex 300, 310, 315. And there is something called ARM virtual hardware, wherein it's a online virtual emulation of the systems, wherein you don't really have to have a actual board. You can just, it's a software emulation of an actual board. You can start developing on that. It's basically an emulated, like, think of it like a digital twin in the cloud. You can start developing it. It's almost timing accurate, but yeah, you can easily run and start developing on the virtual hardware. You don't have to depend upon the actual hardware, and start developing your application, integrate your CI/CD tools into it, start developing that there. And in the end, when you really want to do your sanity checks or on-field testing, deploy the applications on an actual board and test out the ML application. So those are some of the FPP and AVH that you can easily use to accelerate your ML application development and ML application development. Another thing that ARM provides is something called a Vela compiler. So it's a different kind of compiler that it's basically optimizes your machine. It's a hardware aware optimizer for your machine learning models. So you can, once you have your quantized machine learning model for inferencing, you can run it through the Vela compiler, which is again open source. And it will generate a code that is optimized for ARM-based MCUs. And if there is, if you configure, say that the actual board has a Ethos NPU, it will also optimize it for Ethos U and NPU. Another question from Ahmed: can I run virtual target using VSCode? Yeah, you can easily connect to a ARM AVH or instance using VSCode, using the ARM device manager, connect it to your AVH target, and you can deploy the application directly over there. So another thing that is really happening, all this was till last year. Now MLOps has really been picking up, wherein it's a basic necessity for any machine learning model to optimize it, right? So unless you deploy it in the field, what if it's not performing to its extent? You just have to keep on refining your ML models. So ARM also offers some MLOps tool. So you can, as I mentioned, using AVH and FPP, you can train the model using on a cloud. You don't have to deploy it every time onto the device. You can keep on training it and see at what inferences it is giving out, and retrain the model. And data collection has to be done on. So for data collection, ARM has come up with something called the synchronous data stream that I was mentioning earlier. It's a standardized way of capturing the data in a stream format. So you have different sensors. You don't have to upload the data using standardized JSON or XML format. Those are heavy on the device as well as on the network. So you can have this, you can integrate this STS format into your target, into your firmware. It will record the data over an STS stream. You can get those STS streams from the device, and then use those things to train and develop your model on an AVH or a virtual platform per se. And once you are satisfied with your model, you can deploy it again for testing onto the actual hardware, and then get the accuracies and the numbers and that thing. So this really accelerates and improves the machine learning process. So yeah, that's it from my side. Any questions or follow-up questions in this till now?
First of all, Varun, thanks so much for your great speech, and also to take care about all the questions. You answered most of them. Let's take a little bit of time to answer also new ones that are appearing. Also, I have a couple of questions. So one question, Joseph is asking, do you have a link to the ML data flow architecture?
So as I mentioned, you can look at the ML evaluation kit. You can just basically Google it, ML evaluation kit. Will direct you to the web page of ML evaluation kit. It provides very detailed information about the evaluation kit and the architecture that I shared with you earlier during my slides. And the slides will be available soon, right, Danilo? For reference for the audience.
Say again, sorry.
The slides will also be available, right?
Sure.
Yeah.
In the next day through the tinyML forum.
Yeah.
Varun, I have a couple of questions. Maybe are of general interest. With respect to the various application domain, how do you see CMSIS used in various industrial domain or application domain? Are there some dominant respect to the others?
So recently, to my experience, most of the silicon providers, they have some CMSIS packs for their devices. They are developing it, and as an I even cannot comment more on that. The industry adoption is picking up on CMSIS, as you mentioned. As you can see, it's been in since 2008, and with more of ML ops and other facilities added, the traction is picking up, and I can see a lot of people using the VSCode extension and CMSIS packs, etc.
Okay. And, especially in automotive domain, ASIL compliance is required. Do you see challenging the subject with respect to CMSIS?
So, I mean, it's all the application code that has to be functional safety certified, right? I mean, the CMSIS pack is just a framework or an open source standard. So the device support pack, they have to certify that it is functional safety compliant, and the application developer has to go through the certification process. So yeah, we are making some effort of having some functional safety compliant CMSIS packs, but I'm not pretty sure about it. I can get back to you.
Okay, thank you, Varun. Joseph just put a link in the Q&A. Is that correct, I think?
Yes, that's right.
Okay.
That's where you go
Good.
to get the ML evaluation kit. It's basically all the source code for application development, the APIs and everything. And it's also available as a CMSIS pack if you want to go through the CMSIS pack route.
Very good. Thanks again, Varun, for your great speech. It was really of great interest and was subject of many questions. Thanks for your time and to also take care about all the questions. So first of all, thanks again to the tinyML strategic partners, because thanks to them, and also thanks to the efforts of the tinyML Foundation, tinyML talks can take place regularly and enable persons like Varun to share their knowledge and their developments at the benefit of everyone. So the strategic partners are AIZ, Arduino, ARM, BrainChip, and Gimpulse, Embed UR, Efficient, Green Waste Technology, Grovity, IMAX, ImageBob, Infineon, Inatera, Not AI, NXP, PMG, PMIC, Polytechnology, Corvo, Qualcomm, Renesas, Schneider Electric, Sensimil, Sony, Silicon Labs, ST Microelectronics, Synaptics, Sentient, and TDK. The executive, let me remind the executive strategic partners, which I already mentioned, Qualcomm, Sentient, the platinum strategic partners, Embed UR, Sony, the gold strategic partners, ARM, Gimpulse, Infineon, Inatera, Renesas, ST Microelectronics, Synaptics, and the silver strategic partners, which I already mentioned and are listed here. So thanks again, Varun, for your time. Really appreciated, and I think also the people attending express gratitude for your talks. Thanks again for your time and your availability. And goodbye to everyone until the next tinyML talks. Bye.
Thank you.